Great. So my final project deals with extending Bayesian multiple linear regression with directed acyclic graphs. I'll say more about what directed acyclic graphs are, but first, for some context, we wrapped up our final unit talking about Bayesian multiple linear regression. So we now know how to use things like DAGs to find posterior distributions for slope coefficients and then run diagnostics and do posterior predictive checking and so on for Bayesian multiple linear regression models. As a refresher, right, the basic formulation is that we're conceiving of the mean for each observation as a linear combination of our predictor variables. And each of those betas themselves has a distribution of possible values. So we're weighting by coefficients, which themselves have distributions. And so for my project, I wanted to continue investigating Bayesian statistical methods and learn different ways to apply the statistical framework that we've encountered. And so I read chapters 1 through 6 of this textbook that I'm a fan of, Richard McElry's Statistical Rethinking, which is a Bayesian course with examples in R and Stan. Stan is a software somewhat similar to DAGs that enables you to do things like Gibbs sampling, Markov chain, Monte Carlo, and so on. So all the examples are drawn from this text. And the motivation that I want to have here is that when we're doing statistical modeling, when we're running a Bayesian multiple linear regression, we're just picking up associations, right, between the variables in our data set. Unless this is an experimental design that is especially carefully well run, we can't say much about causation at all. And so to me, the key question was, well, can we use Bayesian methods to learn about causal relationships? And it seems that in some cases we can. So this is a good time to introduce directed acyclic graphs, or DAGs. These are graphs, right? They have nodes and connections. So if you look at the picture below, the nodes are A, M, and D, and the connections are the arrows. They're directed because they are trying to describe the connections of causality. And so if we have this arrow from A to M, that means A influences M causally. And they're acyclic. There's no recursion. That is, they do not allow causality to go back and forth. So these are causal graphs. And in this example, we're looking at the average age of marriage, the marriage rate, and the divorce rate by state. And so this directed acyclic graph shows a situation in which you have age directly affecting marriage rate, or average age of marriage directly affecting the marriage rate. And both of these causally affect the divorce rate. So there are some packages you can use, but I won't dwell on that. Here's another example. So in this directed acyclic graph, the average age of marriage influences directly the marriage rate and the divorce rate. But the big difference, of course, between this and the last one is that the marriage rate no longer is thought to causally affect the divorce rate. So these are sort of representations of hypotheses that we might have, right? Ways of thinking about the way that variables relate to each other. And so these really, again, are questions of causation. So suppose you have this hypothesis, right? You think this DAG might be representative of reality, and you also think this DAG might be representative of reality. Well, how could you figure it out, right? How could we identify these causal questions using multiple linear regression? And that's the first thing I'm going to talk about, which is combining directed acyclic graphs with multiple linear regression models from a Bayesian perspective to infer causal relationships. As before, when we're doing this sort of statistical math modeling, like really all we're doing is associations unless we're in an experimental setting. And so as an example, suppose we ran a simple linear regression model in a Bayesian framework using average age at marriage as our predictor and divorce rate as a response. So we might end up with like a pretty big coefficient on average age at marriage per state. But we could just totally be picking up this mediated relationship wherein the relationship between A to M is super strong, and then M to D is super strong, but A to D is quite weak, right? And so despite it being the case that statistically it looks like there's a really strong relationship between A and D, causally there's a really weak one. And so this is somewhat troubling from a causal inference perspective, and is one reason why you typically don't want to read too much into statistical inferences. With DAGs, I think we can do a little bit better, right? So we can look at the implications of the models and then see if they're consistent with our data. And the way we will check that is with multiple linear regression. So we'll call these testable implications, and then we'll seek to test them. So I want you to compare this DAG with this one. The key feature between the two, of course, is that in the second one, marriage does not causally influence D. And so a testable implication of this model then is that knowing A, is that once we know A, rather, knowing M tells us nothing more about D. And the reason for this, of course, is that the reason that M is associated with D is purely statistical. It's purely probabilistic, right? Because it is connected through A. And so consequently, if we condition on A by including it in our multiple linear regression model, along with M, then we can see if this implication is false, right? We can falsify this DAG. For instance, if the coefficient, or if the beta coefficient posterior distribution for M is not around 0, that would indicate that in fact, if we know A, then learning M still tells us something about D. And so this DAG probably isn't right. And so yeah, we can just implement this in DAGs, which is really useful now that we know how to do that. And I guess I want to highlight that the key question that multiple linear regression is helping us answer is there any additional value in knowing a variable once I already know all of the other predictor variables? And so here that means after I know the marriage rate, right, is there additional value in knowing age of marriage? Or if I know the age of marriage, is there additional value in knowing marriage rate? And so the basic sort of thought here is that we might want to know the relationship between some response variable and some explanatory variable. And we can construct DAGs out of these variables, and they will give us testable implications. And so then instead of simply running a multiple linear regression model, let's say, and then like looking at the coefficients and seeing what we think, we can fit a bunch of different models that will test the implications because we understand the causal mechanisms that we're hypothesizing and investigating. And then we can falsify them and continuously improve our knowledge. Okay, so that's the first thing. Here's the second, which is directed acyclic graphs for selecting explanatory variables. You probably heard a lot about problems where you omit an explanatory variable that perhaps is like a latent variable that influences both the explanatory and the response variables. This book also really emphasizes that there are risks to including more variables. The included variable bias is real. Okay, so how does that happen? Well, here are 3 ways that including variables can confound inference. One is if you have high pairwise correlations between explanatory variables. I think probably people already know about multicollinearity, so I'm going to press forward. Second is this thing called post-treatment bias, which I think is quite interesting. So I think this is best explained with this example. If you control for weed presence in your model, when modeling the effect of pesticide on plant height in an experiment, that's really going to block the causal mechanism or the statistical mechanism by which pesticide affects plant height, because the presence or dearth of weeds is the mechanism by which pesticide affects plant height, right? If pesticide works, then it kills the weeds, and if it doesn't, then it doesn't kill the weeds. And so consequently, if you control for weeds existing, then you are just going to block the causal mechanism, and it's going to look as if pesticide doesn't do anything. So this is post-treatment bias. This is easy in experimental settings and harder to see in observational ones. So there's a real danger there. The third is called collider bias. And so I think I've mentioned something related to this previously, where if both a response and an explanatory variable, so here that's y and x respectively, are causally related to z, that is, they are causing something in z, and you condition on z, even though x and y aren't themselves causally related, they will now be statistically related, right? Because knowing something about z does tell you something about x and y. And so it will appear as if there is some meaningful coefficient on the explanatory variable x with respect to y. But in fact, that's merely a figment of including this collider variable. So these are the 4 elementary directed acyclic graphs that illustrate confounds. I think these should look somewhat familiar to you. So in the fork, right, that's where you have some spurious relationship. In the pipe, that's the mediated relationship, and that's similar to the post-treatment bias problem. The collider is what we just discussed. The descendant is something of a special case of the collider. And so these are all things to watch out for when you're writing DAGs and trying to model things. So I think the uses of this will become more clear in this example that follows. But the basic algorithm here is that we want to identify all the possible paths, right, that connect our response or our explanatory to our response variable. And then for each of those paths, we want to see if any of those paths are open or closed. If there is a backdoor path, which is when a causal arrow is entering our main explanatory variable of interest, we want to take note of that. And then we want to try to close all those backdoor paths because those will be confounding. Cool. So here's an example where we have a slightly more complicated directed acyclic graph. So well, I guess the question we want to understand is the causal effect of Waffle House density on divorce rates in a state. So obviously, I think there's no causal relationship here, or at least on first blush, it seems sort of straightforward that we'd be very unlikely to expect a causal relationship here. And so, yeah, we have, as before, A, M, and D, right? The average age of marriage, the marriage rate and divorce. We also have W for the number of Waffle Houses per capita, and S as an indicator variable for being a southern state. And so, as before, we want to identify, right, the open backdoor paths. And so what that involves is looking at anything that gets us to W. And so there are three ways then that we can go from D to W that aren't just this one causal path. And so we need to watch out for those in our modeling. So the first way is we could go this way, so from D to A to S to W. We could also go from D to M to S to W. And I guess we could go, well, I think there's a third and it's written on the slide next. So we'll go there. Right, DMSW, DASW. Oh, right, okay, and DS and W, because, yeah, right, okay, cool. And so, yeah, in all three cases, the key thing to notice is that the path runs through S. And we want to close this. And so therefore, we can just condition on S and close all of these backdoor relationships. So now our multiple linear regression model will in fact answer the question, what additional information about divorce rates do I learn, provided that I already know if the state is southern? And that's good because the fact of a state being southern or not is causally related to divorce rates, but it's mediated right through the average age of marriage and the marriage rate on the divorce rate. And so this is like a nice example, it's a clean example. But of course, this isn't always possible. Causal inference is really hard, and this requires not just good statistical knowledge, but also like being able to draw these graphs and generate testable hypotheses, and also just like a lot of scientific knowledge. So this isn't always possible. You're often going to have unobserved variables, but at the very least, you can sort of understand better when to include which variables and when to exclude them. And that's roughly the conclusion. Responsible, accurate use of statistical methods for causal inference is just super, super hard. But I think that directed acyclic graphs and Bayesian multiple linear regression can help us do that.